Okay, so let us start my last lecture. So let me first remind you what we did yesterday in the second part. So I reviewed the traditional formulation of hydrodynamics, for which the equation motions are just the conservation equations. Okay, conservation of the stress tensor, and if you have any conserved charge, and then there will be a conserved current. And so the basic idea is to express the stress tensor and any conserved current in terms some dynamical variables. And the most natural variable to use, say, are the local temperature and the local chemical potential, and also local velocity field. Okay, and so these are variables. So these are the right variables to account for the right number of equations. And then the task becomes simple. Then you just write down the most general local expansion of the stress tensor and the current in terms of those dynamical variables. Okay, and with the leading term given by the equilibrium expression. Okay, the leading term given by the equilibrium expression, and but you also have to impose, and then when you go to higher order terms, so T mu will be expressed in terms of beta mu x, local chemical potential, and the velocity field. Okay, then the rest just become a tensor analysis. So you expand into the first order, the zeroth order, just the just equilibrium expression, okay, and this is normally called ideal fluid, and then you will have higher order derivative corrections, okay, and in those derivative corrections, of course, there's a viscosity, for example, shear viscosity, bulk viscosity, and also if you have a current, similarly, and then you will have, say, conductivity. Okay, so these are the dissipative coefficients, and then you will have many other similar transport coefficients. And so key is that actually this derivative expansion is not complete. You actually have to impose various phenomenological constraints. And for example, the quantity appear here, and here should satisfy the standard thermodynamic relation, and also there should be a non-active entropy production, and also there's an Onsack relation. Okay, the phenomenological constraint is that the first law, and then the second law. So the second law will impose that actually eta, kappa, sigma all greater than 0. And also there are some equalities. Okay, for example, some terms are just not allowed, and there are also some equality among different coefficients. And then the third one is the Onsack relation. Okay, Onsack relation. So you have to impose those constraints, and then you have a complete formulation. Okay, then essentially a complete formulation. So it's formulated as equation motion. So as formulated as equation motion. So those equations by itself, they don't capture fluctuations. Okay, and there's a simple fix when you are near the equilibrium. Then there's a simple fix, is that you just add some stochastic terms on the right-hand side. say, you add some stochastic terms on the right-hand side, and then you require those stochastic terms satisfy the Gaussian fluctuations. Okay, and again you just follow in the Brownian motion, requiring the fluctuation, the moment which the Gaussian fluctuation parameter then relates to those viscosity. Okay, so that's the standard treatment to include the fluctuations. And but this treatment works very well if you are only interested in the linear, say, perturbation around equilibrium. Actually, this captures the full story. But if you want to go to nonlinear story, or if you want to go to the non-equilibrium situation, far from equilibrium situation, then it's actually not clear how you write down this stochastic force. And also, it's not clear how you write down their fluctuations. Okay, because now their fluctuations will depend on whatever non-equilibrium situation you are in. Okay, so it's not then there's no first principle tell you how to do that. So so this is the main motivation. We want to really develop this hydrodynamics really as a general effective field theory, and then we can just incorporate all those things systematically. Okay. So now let's try to do it. Let's try to do it. So now let's really write down an effective field theory for fluids. So since all the slow variables are associated with conserved quantities, and then it's natural when we consider generating functionals, we just consider the sources depending on the source corresponding to the stress tensor and the current. Okay, so that means the source for the stress tensor is the external metric. Essentially, you put your space-time in the curved space-time. So you have two copies of them. So G1 means the metric on the first copy, and then you can also have an external gauge field for the external source for the current, which I call A. Okay, so then you have G2, A2. Okay, so this is the generating function we are interested, and we want to express it in terms of some slow variables. Okay, and their effective action. Okay, and their effective action. Okay, the effective action. And yeah, again, this is just describe this contour, but now you have G1, A1 here, and G2, A2 here. Okay. And so now the immediate question is that what is the precise choice of those slow variables? Okay. So in this case, when we write this phenomenological theory, the natural choice is the temperature, local temperature, chemical potential, and velocity. But actually, if you really want to write them as a path integral, you quickly realize actually they are not suitable in such an action formula, in such a formulation as effective action. The reason is very simple. Yeah, there's various reasons. First, people have tried many years. It's hardly, they could not really do it. And also another reason, another reason is that when you look at the equation motion for those variables, okay, actually they're first order. So rather than normally, say, if you have a scalar or Maxwell theory, they are second order equations, and you find those equations actually first order in terms of those variables, only contain first derivative. So the leading order term is first derivative. Okay, and we know that the first order derivative equation with first order derivative is rather awkward to write them in terms of action formalism. Okay, and so analog would be the Maxwell theory. So when you write the Maxwell theory in terms of electric and magnetic fields, and then of course equation motion are first order in derivatives. And we know when you want to write the Maxwell theory as a more fundamental theory in terms of action principle, and then you actually should not use the electric and magnetic field as action principle. You should introduce the potential. Okay, so here it's the similar idea, and somehow we need to find the analog of the vector potential for those variables. Okay. So now then what should we do it? So we have some clue. We have some clue how to do that. So let me first consider a simpler case. Let's not worry about the stress tensor. Let's just worry about the current. Okay, just imagine we have a conserved current, and then in this case, then we just have a generating functional A1, A2. Okay, A1, A2, and they are just formally I can write it as rho 0. Then again pass ordered IA1 mu J1 mu minus IA2 mu J2 mu. Okay? Yeah. So let me just make a few remarks on this generating functional. So first is that the W must be non-local. So as a function of A1, A2 must be non-local. And the reason it's non-local is very simple, because we have argued before, for any conserved quantity, they are always slow modes, slow gapless modes. And when you integrate out those gapless modes, of course, then this will be non-local. Okay. But that also tells you if you have identified, conversely, if you have identified the right hydrodynamic modes, okay, then this S effective must be local, okay, and S effective must be local, because the only reason for the non-locality here are those gapless modes which we want to extract at low energy, okay. So this is one comment, and another comment is now because of this current are conserved, okay. So we have two copies. So those currents are independently conserved, okay? They're conserved along each copy. So that means actually then this generating functional should be invariant under independent gauge transformations of A. Okay, should we satisfy A1 plus d lambda 1, A2 plus d lambda 2. And lambda 1 and lambda 2 are some arbitrary functions, okay? But we assume, so these are the small gauge transformations. We assume they all vanish at infinity, okay? As both time infinity and spatial infinity. Okay, so this generating functional should satisfy this. So now what we want to do is use this as a clue, okay? Now we want to guess. Okay, we want to guess what should be the dynamic variable here. Okay, we want to, in other words, we want to integrate in. Okay, we want to integrate in from here, from this generating function of which those modes have been integrated out. Now we want to integrate them in. Okay. Yeah, it's because because they are always gapless modes associated with the conserved quantities. And whenever you integrate out those gapless modes, then there will be non-locality. So if you have identified those right modes, and then the rest should be local. Okay. So now let's just integrate them in. So let's now try to integrate them in. So normally, in quantum field theory or condensed matter system or many body system, integrate in is a very hard thing to do, because there are just too many possibilities. Okay, normally don't integrate in, but here we actually have lots of clues. Okay, here we have lots of clues. So the first clue, we say again, just to emphasize again, S effective should be local, and the second clue is that this gapless mode must appear in this effective action in a way to ensure, so let me call this equation, to ensure this 2, okay? Okay, to ensure 2. So whatever is the gapless mode, this has to be ensured, okay, at a fundamental level. It should not depend on any details, okay? So the third one, the third clue is whatever the Laplace model you choose, the equation motion for chi must be equivalent to the current conservation. Okay? Because the only information we have is current. The equation motion we want to derive must be the current conservation. Okay? So that means the equation motion of chi must be equivalent to the current conservation. Okay? In order to find the right modes. And the last is that this procedure, this choice of chi, should be universal. So this is really a blessing, because the fact that the conservation law will lead to the slow variables. This statement does not depend on any details of any individual systems. Okay, so you must be able to guess what are those modes without knowing any details of individual systems. Only based on conservation. Okay, so that's the reason somehow we think this problem is doable. Okay, it's doable because it should not depend on any details of any individual systems. Okay, so now with this ABCD, now we can just guess it. Okay, I will just write down the answer for you because it's a very easy guess. Okay, it's a very easy guess. So so A to D can be satisfied provided let's write the path integral in the now let's try to write this into a path integral. Now I postulate the existence of two scalar fields. So here chi just collectively denotes the slow variables. Okay, so now I'm being more specific. Now here the slow variables are two scalar fields. Okay, are scalar fields, and this effective action now is only a functional. It's a local function of B1, B2, and B1 and B2 are defined as following. Okay, so B1 mu would be A1 mu plus partial mu phi 1. Okay, and similarly for 2. For subscript 2. Okay, so this is the proposed answer. Okay, so suppose I consider some scalar fields and require my action depend on this scalar field and the external field and the external field A only through this particular combination, then all these conditions can be satisfied. Okay, then all these conditions can be satisfied. Yeah, so let's see. Okay, so let's see. Yeah, first we just require this to be local. Okay, we just require this to be local. And then to see the 2, okay, to see that this is satisfied, is very simple. It's because the phi can be considered integrating over phi can be considered as integrate over all possible gauge transformation of A. Okay. Now, whenever you do a gauge transformation of A, then you can always absorb into phi. Then of course this will be satisfied. Okay, automatically satisfied because you can just absorb it into phi. So 2 is satisfied. Okay, so 2 is satisfied. So now let's look at 3. So let's look at C. Yeah, let's look B is satisfied. Now let's look at C. So to look for C, so let's look at the equation motion for chi. So this can be any local function of B. Okay, it does not depend on the details. So let's look at the equation motion, for example, with chi 1, with phi 1. So this is the same as the derivative acting on B. Okay, and on B, take derivative over phi 1. Okay, and this by definition, and the first one just becomes the derivative over A, because B is just equal to A plus that. And the second is just a total derivative. Okay, just you can put derivative here. Yeah, the case one is just a total derivative, then you can just integration by part. Okay, and this by definition is the current. So now we have a conservation of the current. Okay, so this equal to 0 means this equal to 0. So that means the phi equation motion just is equivalent to the current conservation. Okay. Good. And so yeah, so I think that this slash said this. So we identify the phi then as the hydrodynamic modes associated with the conserved current. Okay. Any questions about this? Yes.
So is it always true that you just the hydrodynamic modes are just like the gauge parameter?
Yeah. You just promote it. You just promote the gauge parameter into dynamic field. And so this is also called the Starkberg trick. Yeah. Yeah. Good. So yeah, so here is the lesson. You just promote gauge transformation, gauge parameters. So this gauge parameters, of course, for the is due to the is for the external sources. Okay, gauge parameters of sources into dynamic field. Okay, so now let's do the stress tensor. Okay, so now let's do the stress tensor. So let me just do it separately, the stress tensor. Okay. So now the stress tensor, yeah. Now the stress tensor again, the analogous equation to this one is individual diffeomorphism because the two stress tensor associated with two legs are individually conserved. Okay. So now we should have individual diffeomorphism. Okay. So now this should be invariant under some diffeomorphism. Okay, so psi 1 and psi 2 denote some vectors which generate the diffeomorphism. Okay, so now the conservation of the stress tensor implies that the generating functional should be individually diffeomorphism invariant. And so write it explicitly. Say the G1 psi 1 corresponding to you. Yeah, it's a standard diffeomorphism. Okay, let me just not write it down. Okay, to save time. Okay. So now again, what we want to do is promote this gauge parameter into the into dynamic variables. Okay, into dynamic variables. So then we can just write down. So now the proposal for the hydro mode associated with the stress tensor. Then we say it should be given by the following. So this is, so now I introduce two vector fields, say depend on some coordinate sigma. Okay. Actually, I need to, sigma. And then I require the action only depend on the external metric and this dynamic field in the following manner in terms of H1, H2. And H1, so H1 AB sigma is equal to G1 mu X 1 sigma partial X1 mu partial sigma A partial X1 mu. Okay, so this is just a diffeomorphism. So this is just a diffeomorphism transformation of G1, and now I just promoted this diffeomorphism parameter into a dynamical field. Okay, into the dynamic field, and then I require that the action only dependent on the combination of this thing. Okay. Okay, so and similarly for 2. Okay, you just replace the similarly for 2. Okay. So this is proposal. Also, I need to do a little bit more. Okay, so I need to actually add additional scalar field, which later I will interpret it as a local temperature. So let me just also add a scalar field here. Okay, and the idea to introduce x just come from here. Okay. Good. So again, let me just make some remarks. But before I do that, do you have any questions regarding this? Yes. Yeah. No. G1 is depend on the x. G2 depend on your physical coordinate x. Okay. And now then I just promote. And then I just make a diffeomorphism from x to some capital X, to the capital X, and just become like that. Oh, sigma I will explain. Sigma. So yeah, I will explain in a moment. Yes.
So this somehow looks different from the way that you were treating. Like why is it?
So this is the analog of the B. So this is exactly counterpart of B for the diffeomorphism. The way to see this is following. So B have the feature that any gauge transformation of A can be absorbed into phi. Okay. So B is invariant on the gauge transformation of A if I transform phi simultaneously. So this H have the similar feature. So when I make the diffeomorphism in G1, that diffeomorphism can always be absorbed into X. Yeah, can always be absorbed into X. And so that's precisely the analog of that. Yes?
So the tau field doesn't follow from gauge symmetry?
No, it does not follow from gauge symmetry. In the gauge field case, you don't introduce, because in the gauge field case, there's no in the gauge field it's just current. There's no local temperature. There's no lotion of the local temperature. Yeah, because local temperature is related to the energy density, fluctuation is related to the stress tensor. Yeah, you will have a chemical potential. I will explain how the chemical potential emerges, but you don't have to introduce separately. Yeah, temperature is a weird thing. The temperature, you don't have to introduce it, but it's convenient to introduce it. Yeah, there's a way not to introduce it, but the formalism is a little bit cleaner to introduce it. Yeah. Yes. Oh, sorry, sigma. Thank you. Okay, so now let me explain the sigma. So now I explain the sigma. Where does the sigma come from? So first, now in order, okay. So now essentially we just promote the original space-time coordinates into a dynamical variable. Okay, into a dynamical variable. But the original space-time coordinate become a dynamical variable, then that dynamical variable have to depend on something else. Okay, so that's the reason we introduced the sigma. Okay, that's the reason we introduced sigma. So somehow the price, so to make space-time coordinates dynamical. Okay, so leads to actually a new emergent space-time sigma, because the which are labeled with A. Okay, so the sigma have the same dimension as the original space-time, the same space-time dimension, and but now I have to introduce this sigma. Okay, and now this action, so this effective action lives in the sigma space. Is in sigma space. Okay, it's in sigma space time. Okay, so again, this equation, if I call this star, is automatically satisfied satisfied as the diffeomorphism of GS. So S will take value 1, 2, okay, can be absorbed into integrations of X. Of XS. Okay, so S equal to 1, 2. So now the calculation is slightly involved, but it's actually fun exercise to check yourself that now if you do the variation of the action with respect to x1, okay, you precisely find the conservation of the stress tensor for the first line, for the first part of the contour, and then similarly for x2. Okay, and actually, the fact that this works for this kind of theory was actually known since the 70s. So this kind of theory, not in this kind of precisely form, was actually used by people in the 70s as a toy model for quantum gravity. As toy model for quantum gravity. So essentially, they want to say, they want to find some toy models for diffeomorphism invariant theory. Okay, and this kind of theory just is like that. It's like that, and people call this parametrized theories. Called the parametrized series. And then people already observed in the 70s that for parametrized series, the equation of motion is always equal to the conservation of the stress tensor. Oh, yeah, it's always smaller because we only need to have the right equilibrium for the equation of motion, not for the components of the stress tensor. It's the same here. The number of the equilibrium are smaller, of course, than the stress tensor itself. Yeah, the number field should be mapped to the yeah. Okay, so now. That one. Yeah. So now the trivial you can combine. So here I treated the gauge field, treated the current and stress tensor separately, and the trivial to combine them. Okay. And JMU together. Okay. And then what you get the effective action of H1, B1. H2, B2, but then I only introduce a single tau. Okay, introduce single tau. So this tau, the introduction of tau, I should admit is a little bit phenomenological. Okay, so I have to put in by hand. Okay, so and this tau will be interpreted as the tau will be interpreted as we will see so tau, so we will interpret the local temperature as some reference scale exponential minus tau. Okay. So this T0 doesn't matter. You just introduce a unit. Don't have physical meaning. Okay. Yes.
So for the phi gauge parameter, when you combine them, does it also couple the X field?
Yeah. So you have to write this in a way. In the diffeomorphism invariant ways. So essentially you have to pull back this into this sigma space. That's right. Yeah. So you have to pull back this to. So the B now is defined on the sigma space, and now you have to pull them back to the sigma space. Yeah. So that's how you combine them. Good. Now let's think about what's the physical interpretation of sigma. Okay. It's a little bit weird. We have to introduce this sigma. Okay, and so we will so the interpretation of sigma A. So our dynamic variable are x1 mu sigma and x2 mu sigma. So we will integrate the sigma mu as the sigma a as the following. Okay, so let's separate sigma a into the time component and the spatial component. Okay, spatial component. Okay. So now we will interpret. So here is the key. Okay. So here we will interpret sigma I, the spatial parts of sigma, as labels of fluid elements. Okay, so you just consider continuous medium of the fluid element, and for each fluid element, you go to the co-moving frame for each fluid element, and then you give a label. Okay, and so each fluid element gave a label, and because the fluid element fills the whole space, and then this fills the whole space. Okay, and the sigma 0 will be interpreted as the clock. Just some internal time for fluid elements. Okay, for fluid elements. Okay, so sigma 0 interpreted as the internal time for the fluid element. So now this has a very simple physical interpretation. So now this has a very simple physical interpretation. So we have this fluid space-time. So now let me call this thing a fluid space-time because of this interpretation. So now, this is sigma a. So suppose this is a sigma 0 direction, okay, and this is the sigma I direction, okay. So now let's imagine, and this is the say x1. This is the x1. This is the physical space coordinates, and this is the second copy of your physical space, because we have two copies of them. And now x1, capital X1. Just map the fluid. Just map this fluid element into the physical space-time. Okay. In particular, let's imagine a situation. You consider you fix sigma I. Means that you fix. You follow a particular fluid element, and then you change sigma 0. So this is just the word 9 of the fluid element. Okay. And then this xi mu sigma then describe a trajectory in your physical space-time. And that is the trajectory of that fluid element in the physical space-time, okay, in the first copy. And similarly, this will be mapped to another copy in the second space-time. Okay? So that will be the physical interpretation of this x1 mu, x2 mu. So phrase into this language. And then this this variable is nothing but the so-called Lagrange description of a fluid. Okay, as a Lagrange, maybe 300 years ago, already figured out this is the best way to think about the fluid, and somehow we are using some fancy integrated informalism. We just recovered that. Okay. We just incorporated that. Yeah.
So, if trajectory in this
Yeah, you are asking whether this function is single valued.
Yeah.
So, for in the path integral, of course, you integrate all possibilities, and but when you solve for equation, classical equation motion, and you always it's always be single valued, and some physical trajectory, and the perturbation around those trajectory will also be well defined. But in principle, in the path integral, I'm not sure how to interpret those weird non-single valued functions. Yeah. Yes. So x1, x2 are scalar field in the sigma space. Yeah, they transform as scalars. Yeah, as D scalars. So this is a little bit like the in string theory, the sigma model. the target space coordinates on the worldsheet. Yeah. Yes. Yeah, you can think it this way. To think about it does not depend on whether you think about specific solutions or just think about the possible trajectories. So this is like possible trajectories. Yeah. Yeah. For example, one of the for example, equilibrium configuration, say in thermal equilibrium, will corresponding to x mu equal to sigma. That's right. That is identity map. And of course, the standard Lagrange formulation, which is normally for non-relativistic fluids, they don't have sigma 0. Okay. They also they don't have sigma 0. They don't have sigma I. But for the relativistic situations, it's natural to have also sigma 0. Okay. So this picture also makes it clear. Okay, makes it very natural for us to derive what would be the velocity field and the local chemical potential. Okay. So now let's just focus one of such word lines. Okay. So if you just follow one of such word lines, and then in the space-time, the proper time along the word line would be, say, g1 mu. So here, partial x1 mu, partial sigma 0. Okay, because we are fixing x sigma I, partial x1 mu, partial sigma 0. Okay, and the sigma 0 square. So this is the proper thing along the space-time, along the empirical space-time. So then we will define the velocity, the corresponding velocity u1 to be just delta x1 mu. So the motion in here divided by this proper time. Okay, divided by this proper time, and so that's by definition. Okay, and so this is same as B1 partial x1 mu partial sigma 0. Okay, so B1 is just defined to be minus g mu mu partial sigma x1 mu partial sigma x1 mu. Okay, so and by definition this u1 is properly normalized. Okay, so u1 square is equal to minus 1. Okay, so this is the mu is in this physical space-time coordinates. Okay, so by definition this have so this would be the correspondence of the velocity field. And similar you can do for u2 mu for the velocity associated with the second copy. And also now there are also two copies of the chemical potential, and the local chemical potential. So we define the local chemical potential as, say, for example, associated with first copy, as again as the time component of this B, and the 0 component. Okay, 0 component, but we also divide by this B1. So this 1 means let me just B0. Let me put 1 upstairs. Okay, it just 1 is associated with this 1 2 index, and also divide by B1. And so the reason to divide by B1 is just again to convert into proper time. Okay, again to convert the space-time proper time. And so this is the definition. Okay, so similarly for two variables, so the velocity and so now we see in this formalism, indeed the velocity and the chemical potential emerges as some kind of derived quantities, some composite field. Okay, just like the field strength in the Maxwell case. Good. So now we have identified the degrees of freedom. Now we have identified degrees of freedom for this for this fluid. And so the next step is to write down this effective action explicitly as a function of those variables. And then now we have to impose symmetries. Okay, so now we have to impose symmetries. Now let's impose symmetries. Okay. So first is that all the specific symmetries of an individual system does not matter, because stress tensor, it just the only thing relevant is those symmetries which are universal for all systems. Okay. So right. Okay. So now we have to impose symmetries. Okay. So here there's one important consideration. So far, when I introduce those variables, including this picture, nothing has said anything about the fluid. Okay. So this picture actually applies to any continuous medium, and any continuous medium. So now we have to impose conditions so that this actually describes a fluid. Okay. For example, the current picture can also apply to a solid. Okay, to a solid. And I think in the background you also maybe thought that way about the solids. And so now we have to impose additional symmetries to make sure this is a fluid. And there's also a mathematical way to think about it. Why this is why we have to impose additional symmetries. So if you just start with a general action like this, say a general action like this depends on H and B, and if you do the equation motion, okay, so in general equation motion will depend on the x and the phi themselves. Okay, depend on phi and x themselves. But the fluid are different, because we know, so the equation motion should recover the standard hydrodynamics. In the standard hydrodynamics, a fluid, because they can move around, you should not depend on the individual x and the phi. The equation motion should only depend on the velocity and the local chemical potential, and nothing else. Should not depend on x at all. So if it's a solid, then can depend on x, because then the x will describe the deviation from the equivalent position, say, of a solid element. But for fluid, it should not depend on x itself. Okay. So now we have to impose additional symmetries to really specify it as a fluid. Okay. Any questions about this? And again, I will tell you the answer. So once you write down the answer, and then it's very natural to see why we impose that. Okay. So this theory is a theory defined on the sigma space. Okay, it's theory defined on sigma space. So now I require this theory is invariant under the following symmetries. Okay. First, it's invariant under sigma I, the arbitrary time-dependent reparameterization of sigma I. Okay. So this is the first condition. And the second condition is I require the thing is invariant under arbitrary reparameterization of the sigma 0, and now can depend on sigma I. Okay. And the third one concerns with the B field, that the B should be invariant under a diagonal spatial gauge transformations. So all this I coordinate means the sigma. Now it's all in sigma space. Okay. So now I impose these three conditions. Okay. So now let me explain them. What's the meaning of them? Okay. So the reasoning. So what defines a fluid? So a fluid element, they can move freely, and there's very weak correlation between different fluid elements. Okay, that's because they can. Yeah. So the first condition just means at a given time. Okay, at a given time, we can the labeling of a fluid element, of course, is not unique. You can make arbitrary relabeling. Okay. And this just corresponding to relabeling of the fluid element. And the relabeling of the fluid element, because sigma I just corresponding to label of fluid element. But this relabeling of fluid this arbitrary relabeled fluid element can only be done at one time. Because once now you have moved, okay, and then of course you can no longer relabel them, okay? So this should be only done at one time. And the second, so remember sigma 0 can be interpreted as some parameter to parameterize this trajectory in your physical space-time. And then this just means you should be able to reparameterize that time, okay? And in particular, since different fluid elements are independent of each other, you should be able to reparameterize them independent for each fluid element. So that means this can actually depend on different, for different fluid elements, this can be different, okay? It can be different. Okay, so these two specifies what we mean by fluid, okay? So 1, 2 defines a fluid. Okay. So now let's look at the 3. So 3 can be interpreted as following. So you have a U1 global symmetry, means that associated with each fluid element, you have some freedom to make some phase change, okay? And since it is a global symmetry, the phase change cannot depend on time, okay? It cannot depend on time. And but each fluid element you should be able to make individual different because different fluid elements and their phase change can be independent, and so this phase change then can depend on sigma I, but cannot depend on sigma 0. This is because this is the global symmetry, okay? And so 3 defines the normal fluid. Normal fluid means normal charged fluid. Okay, you have a global symmetry, and then each fluid element have the freedom. Each fluid element are independent of each other, and then you should be able to make the independent phase changes for each individual fluid element. And now, if you do a superfluid, the difference between the superfluid and the ordinary fluid is in the superfluid, the phase of all the fluid elements are locked together now, okay? So for superfluid, it just drops 3. Superfluid, it just drops, just drops 3, okay? Just drops 3. Okay, so that's the story. So so this is for the this is a preferred frame because this is in the fluid space-time. This is in the fluid space-time. So this is all in the fluid space-time. There is we follow each fluid individually. So there is a preferred frame. Because this is in the core moving frame of the fluid itself. So there's no general relativistic symmetry, general diffeomorphism invariance in the fluid space-time, because there is a fluid, because there's a preferred frame when you're sitting on the fluid itself. Yes.
So what would you drop to define a solid?
That's a good question. First, you should drop this one. Because now each of them have the equivalent position, and this one you may still keep. I haven't. I only thought a little bit about solid. I have not really looked at it very carefully. Yes.
So suppose we start with the normal fluid case. Should
Yeah.
we expect some point that
No, that will not be captured in this formalism. So that will not be captured in this formalism. It's because normally when you in the phase transition, you have to introduce additional parameter. Because something have to condense.
right? So there is no order parameter.
If you want to describe that transition, and then you have to introduce the order parameter for that phase transition. and then write the full theory of the order parameter and the hydrodynamic theory, and then you should be able to see that. Yeah. Other questions? Okay, good. Okay. Right. Good. Yeah, actually not good. Again, my notes get a little bit disordered. Okay. Seems I'm missing a page. Okay. Right. So now we add those symmetries, and then we also need to add the constraint. So these symmetries are specific for fluids. Now we also need to add a constraint, which we discussed yesterday, for a general quantum many-body system defined on this closed time contour. Okay. So we still need to add the 1 to 4 of yesterday. Yeah, so let me just relabel them to be 5 to 8. So add 5 would be S effective star equal to S effective, which you switch the minus phi A. Okay, you keep the phi R to be the same. Yeah, let me just still write explicitly. So phi A, phi R. And the 6 is the imaginary part of the S effective, should be greater than 0. And the 7 is the it said when you set the A field to 0, it should be 0. And the 8 is this dynamical KMS. Dynamical KMS which is the which is S effective. So again, this phi just collectively denotes the source and the plus dynamical field, okay, and then acting this Z2 transformation should be equal to phi R, phi A. Okay, should be invariant under this Z2 transformation. Okay. So, and now this gives you a complete formulation. Now this gives you a complete formulation of the action of this action in the exponent. Okay, but there's still some subtleties how we do define this measure. Okay, there's still subtleties how we do define this measure, and I don't think I will have time to talk about it. So let's not worry about that. Okay, so this will give you a complete formulation. And for the S effective, and to define that measure property, yeah, let me just say a couple of words. Define that the pressure property, and then one actually has to introduce some fermionic variables, and so that's where the supersymmetry come from. Okay, but then we'll have to introduce some fermionic variables. So now let me just quickly tell you, and now the rest is mechanical. Okay. And the rest you can hand it to a high school student. Yeah, not quite. Yeah, because you have to do some differential geometry. You have to do some differential geometry. Yeah, but occasionally there would be high school students showing up in our seminar, saying whether they can listen to our seminars in string theory and in string theory. And then after the seminar, they say, "Oh, actually, it's good." Yeah. So then, so don't underestimate the high school students. Okay, good. So now let me just tell you some consequence of it. Okay, some consequence of it. So remember, those are from unitarity. Those are from unitarity, and this from time reversal and the local equivalent. Okay. So now let me say a few words about this before I say the consequences. Okay. So you can So yesterday when I write down this transformation, I did it for rigid. Temperature. Okay, just imagine you have a background temperature. But of course, then in this hydrodynamic situation, then you no longer talk about the rigid background temperature. Okay, so now you only have local temperature, which is captured by this tau. Okay, so the beta x, so beta sigma will be 1 over T sigma. Okay. So now, then this D2 symmetry will generalize as follows. So again, you can write it. Again, we are involving, say, some operation involving time reversal, and then plus a shift in this beta. Okay, but now in the local temperature beta. And but now the story becomes a little bit complicated because we have all this complicated. Because in the even you start with a flat space time in your physical space time, in the fluid space time, because of this non-trivial mapping, you actually have a curved space time. Okay, you actually have curved space time. Somehow the fluid motion now just captured by some curved space time dynamics. And so the story gets a little bit more complicated. Now the time shift. Now you have to shift. Yeah, you have to time reversal, and then you have to shift in this beta. And the beta now you have to use more fancy differential geometry language using the, say, Lie derivatives, etc. Okay. So now let me not go into that. So let me just write down an infinitesimal form, just assuming you can expand it in derivative. Yeah, expand in this beta. Okay. So just give you a feeling of it, and then the diagonal part of x mu sigma just given by minus x mu minus sigma, the diagonal part, and the non-diagonal part, the antisymmetric part of mu minus xa mu minus sigma, then plus I beta mu minus sigma. So here actually I'm taking this theta to be parity plus the time reversal. Just a little bit simpler, so I invert everything. And then the phi tilde, yeah, and similarly with phi tilde, this just gives you a feeling of it. Okay. So beta mu would be this beta sigma times u mu sigma. Okay, u mu sigma. And so this defines some kind of proper local temperature. So this is the local temperature, and this is a velocity vector. This velocity factor, and it's natural to combine them into some kind of proper local temperature vector. Okay, and so that essentially controls the infinitesimal form. So they're higher order corrections. Okay, the higher order corrections. Okay, good. So now let me talk about the consequence of those symmetries. So now let me talk about the consequence of those symmetries. Oh, then another side remark I can make is that in this story so far I talked about this applies for general quantum systems, and so far applied to general quantum systems. And then you can take a classical limit. Okay, you can actually take a classical limit, and but those unitarity conditions actually survive in the classical limit. Okay, actually survive in the classical limit. Good. Okay, so now let me just tell you the consequence of this. So now with this operation, it just become a question of doing differential geometry with those diffeomorphisms. Okay, with those diffeomorphisms. And then you can say for example, you can expand your effective action, say effective Lagrangian, say in terms again in terms of number of phi fields of the antisymmetric phi fields. Okay. So this would be say of order phi a, and this is order phi a square. So A here means just antisymmetrical variables, okay? So phi denotes antisymmetrical variables, etc. And again, there's this term comes with I, and this controls the fluctuations. Okay, this controls the fluctuations. Yes.
I had a question about something else. I just want to have an what is beta to the super's temperature? What does it literally mean locally? Like, it has properties of locally.
Yeah. Locally, essentially, this is a proxy. Say yes, and now let's not worry about conserved charge. Okay, say you only have the conserved stress tensor, and then this beta is a proxy, say, for the local energy density. Yeah, it's a proxy for local energy density. Yeah. Good. And again, you can derive equation motion. Okay, you can just derive from here equation motion by value of x and etc. Okay, and then, as we described before, when you as we described yesterday, when you do the equation motion, you can always set the A field to be 0. Okay, you can set all the A field to be 0 because the A field equation motion of A field automatically satisfied with A equal to A field to be 0. And then when you do that, okay, you do effective action, say with XR mu, then you take all the A field to be 0. Then A will can be 0, and then this to be the A field, and then set A field to be 0. Then that gives you the computation of the stress tensor. Okay? And that gives you the stress tensor. And now you find the T mu mu when you expand it. Okay? Then you find indeed the T mu mu can precisely be expanded in terms of with those symmetries. Okay? With those symmetries. So this is, with those symmetries, then T mu mu can precisely be expanded in terms of velocity field, local chemical potential, and the temperature. And nowhere does x and phi appear. Okay, and you find exactly a standard derivative expansion in terms of velocity field, and thanks to those symmetries. Okay, so you just recover standard. So called constitutive. Yeah, so this is normally called constitutive relations. Constitutive relations. Okay? Yes?
So if we don't set XA 0,
yeah.
we get the system with the current flow.
Yeah, so XA, so at the equation motion level, if you don't turn on the antisymmetric source, then you can always set XA equal to 0. And when you don't turn on the, if you don't set that source equal to 0, then the A variable is non-zero, and then you can then solution will depend on those A fields, and what that gives you is the tree level contribution to the to various correlation functions. Yeah. Okay. Yeah. Okay. So those symmetries. Okay. So those symmetries just give you the standard derivative expansion. And now you find the 7. So now let me emphasize 8. Okay. So the 8. So this time reversal. So the 8. This is the D2 symmetry. Now tell you, okay, that indeed the local energy density, pressure density. So local energy density and pressure density. So you have T mu 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 plus the derivatives, and similarly for J. Okay. So here including the epsilon p as a coefficient, and here including the shear viscosity and the kappa, etc. as coefficient. And here, indeed, you find the local energy density, local pressure density, and the local charge density satisfies the first law, okay? Just satisfies the standard thermodynamic relation. And just come from this D2 symmetry. Somehow miraculously imposing this D2 symmetry and give you those thermodynamic relations, okay? And also, this D2 give you the fluctuation dissipation relation. Fluctuation dissipations. Yeah. So those were also. So those, just as a Brownian motion example, those here captures the Gaussian fluctuations, and so here we also depend on various parameters. Okay. Yeah. When you expand in terms of field, there will be various couplings. Let me call this collection of couplings lambda I. Okay. Lambda I. And so fluctuation dissipation relation, so then you find the local fluctuation dissipation relation, which relates, again, those lambda I with those dissipative coefficients, say eta, kappa, and the conductivity, etc. Okay? And again, this comes from this D2 symmetry. And the third thing from the D2 symmetry is actually give you a full nonlinear Onsager relation. So this fluctuation dissipation relation are only local, okay? Full nonlinear Onsager relations. Okay, nonlinear Onsager relations. And now if you impose imaginary part of the S effective to be greater than 0, and then you deduce those lambda I should be greater than 0, and then that tells you this dissipative coefficient should all be greater than 0. Okay. Should all be greater than 0. Lambda I is the coefficient which appears in the fluctuating terms. Yeah. So when you just like in the Brownian motion, there's only single term, but here there are many terms. Yeah. So there are various parameters, and yeah. Wow. Oh, actually, I'm running out of time. Okay, sorry. So now let me just say the last words. About the second law, okay? About the second law. So now you can also prove a second law, okay? So now you can prove a second law. So now actually one can prove a theorem. So now you can prove a theorem. You said any local effective field theory satisfying. So this is not restricted to hydrodynamics, okay? Any also including, you can see the other order parameters. Any theory satisfy this 5 to 8, okay? In the classical limit, okay? Satisfy the 5 to 8. Actually, there exist a current S mu which satisfies partial mu S mu is always greater than 0. Okay. So you can actually prove a theorem, and then that of course including the hydrodynamic situation. And so let me just say a couple of words where this comes from. Okay. So here we have a Z2 symmetry. So this Z2 symmetry is a little bit different from the standard one because this Z2 symmetry not only involving some kind of reflection of the space-time coordinates, also involving some infinitesimal changes, okay, involving derivatives. So now, because of that, your Lagrangian is only invariant under that kind of transformation. So let me using tilde to deduce to deload the Lagrangian after you add this Z2 symmetry. Okay, just like here, yeah, L tilde corresponding to evaluate the phi tilde field. Okay, so then they differ. You can differ by the original Lagrangian by a total derivative. Okay, by a total derivative. And now you can use the standard Lothar technique. Now use the equation motion in this equation. Yeah, take the difference of them, and then use the equation motion. And in the Lothar case, if you have a continuous current, then you can do infinitesimal changes, and then this just become a conservation of the current. But now, since these are finite transformations, and the equation motion does not completely, things don't completely vanish. But nevertheless, you can derive the existence of some current S mu at the right-hand side is now vanished, non-vanishing. Let me call it K. Okay, now let's call it K. And now the K turns out that the K can be shown now is related to the imaginary part of S effective by an integral transform. And this integral transform is actually positive definite, okay? Okay, by integral transform. And so, and then since imaginary part of S is greater than 0, to this theory, this should be greater than 0. This theory should be greater than 0. Okay, so in here, the entropy current is just emergent. Okay, just such it just follows from this symmetry. And but then you can check. Then when you go to equilibrium situation, then this S mu then turned out to just agree with the standard definition of the entropy. Okay, I just give you the standard definition of thermodynamic entropy density. And yeah, but this will generalize this into this general local equilibrium situation. Local equilibrium situation. And also, let me just make one final remark. In the ideal fluid case, say, so you only consider the zeroth order. Forget about all these dissipative contributions. Okay, so these are dissipative contributions. If you look at only ideal fluids, so this ideal fluid part, as I wrote yesterday, does not involve any derivatives. Okay, because it does not involve any derivatives, and then this kind of sign, this kind of space-time reflection does not matter. Okay, they don't play any role. And if you erase that, and then now this becomes a continuous transformation. And now you just have accidental, now become accidental U1 symmetry. And so at the ideal fluid level, then this now become a conserved current. Okay, become conserved current. And so that just consistent with the standard expectation that in the ideal fluid, the entropy is conserved. Okay. Okay, I will stop here. Thank you. Thanks. Yeah. Yes.
What happens when you restrict your symmetries to a smaller group than spatial bits, like volume derivatives or something like that?
Yeah. I have not systematically explored them. Yeah. Right. Yeah. So yeah. For example, one just the simplest example this can be used is to say, so as I mentioned earlier, when you are near equilibrium and the linearized order, the standard stochastic equation works. So the simplest and then the power of this formalism is really going to say more non-equilibrium situation for example, to a steady state, to a so-called non-equilibrium steady state, or to some expanding, for example, expanding plasma, this kind of situation. And so I mentioned many examples at the beginning, just in the first lecture, and just those cases. Yeah. Yes. Oh, yeah, that's from the unitarity. So essentially, you can, by integrate out degree freedom, you can write this effective action essentially like something like fidelity. And because fidelity is always smaller than 1, and so this just comes from the following thing. Take a wave function, you involve it forward in time using one Hamiltonian, and then involve it back using another Hamiltonian, and then the overlap with the original state is always the modulus is always smaller than 1. Yeah, just follow from that. Yeah, and the reason you go forward and backward, they just essentially correspond these two legs. Yeah. So let me just say a few words about that. So here, so everything works. I said in the exponential, but we have not been very precise about the measure, because whenever you integrate out the things, so if I want to do it precisely, so this exponential corresponds to 1 over h bar. But you could often have other contributions, say of order h bar to the power 0, etc. And then they can be considered as how to define your measure, etc. Okay. So a trick to treat those things is to introduce some kind of ghost variables, and then you can put them also in the exponential, and then they also can be say at the same order of 1 over h bar, and then things just become easy to treat. So now, so when you introduce those ghost variables, what naturally comes with it is so-called BIST symmetry. So then you have one fermionic charge, which is this BIST symmetry. And now it turns out with that one fermionic charge, and now when you have this local equilibrium, now when you impose this Z2 symmetry, and this Z2 symmetry does not commute with that the BIST charge. So that generates a new a conserved charge. Okay, it generates a new a conserved charge. And now you have two fermionic charges. It turns out these two fermionic charges, they commute precisely into a translation into this beta mu. Okay, and into this beta mu. These two fermionic charges, they anti-commute into this beta mu. And actually, we also proved the theorem with Ping-Gao that any theory which is local equilibrium satisfies those. Any theory satisfies this local equilibrium condition. Any bosonic theory satisfies this condition. You can always supersymmetrize it. You can always supersymmetrize it. Okay. Yeah. Okay. Yeah.
So before you all get coffee, we're going to take our group photo now. So like to sort of herd the group. You said barren field, Don?
Yeah.
So this is the big field that's sort of on the way back to Kittredge and C4C. So sort of take the group over there. We'll get a few quick pictures, then we'll come back.
Yes. Okay. Forward.
So, can this model be used as like fluid models for like black holes? To look at like, could you use this to construct like a?
That's right. It might be depends on specific case. It depends on specifically what one wants to do with that kind of fluid model for black holes. Depending on what kind of thing you want to calculate.
But like these effective Lagrangians, can you somehow get like the analog of like Einstein equation for like a fluid or something like that?
Oh, that's a good point. Maybe something like that. Maybe something like that can be made more transparent in this formula.
Because I know there was